Good morning once again. Let me share the screen. Okay. Perfect. So, do you have any question before I start? My usual asking. Thank you. Let me just change to the other screen. I put the Teams window on the other screen so I can look at the chat and I can see if somebody's in the lobby. Okay. As you can see on the screen, this is a list of our links. Let's click on risk-based adaptation design. So on Monday, we introduced the risk equation, which is this one. There is a micro open. If you can please close it. Otherwise, I need to look at the micro that is open. Okay, it seems that now it's still open. If you can please close the micro, I get now the person who has the micro open. Merad Alega. Okay, I close the micro for you. Okay, good, thank you. Perfect. So risk estimation, as I said, we introduced the terms of this multiplication. It's a very simple multiplication. The three factors are probability, which is frequency of the considered event, and probability is given the symbol P, and then we have vulnerability V and exposure E. We also said that the units of R is the risk, is given by the units of exposure. If exposure is measured in monetary terms, we get the risk in monetary terms, and so forth. So let's consider that R is the risk that we get in the considered time period. So if the probability is in fact the probability that we get an assigned event in a given year, then R is the average risk that we get during the same time period of 1 year. Okay, so it depends on the time window the probability is expressed. So if again probability is considering the probability of the event occurring in 1 year, so the time period is 1 year, then R, the result of this multiplication given by equation 1 here, it's the average risk, the average damage that we get in the same period of 1 year. So R is the damage that we expect in the same period of 1 year. You understand that if the probability is low, then you have a low expected damage. And if vulnerability is large, you have a high expected damage. And if exposure is large, you have also a high expected damage. So basically, what is the event that we may consider? For instance, the probability of occurrence of an earthquake of a given intensity, or the probability of occurrence of a flood of a given intensity, a flood for a given extreme river flow. And look, if you are interested, for instance, in a flood, the probability is given by the probability of exceedance of a given river flow. So let's suppose that the flood starts at river flow equal to 1000. 1000 is the intensity of the river flow. Then we are interested in the probability that 1000 is trespassed. We are interested in the probability that we have a river flow greater than 1000. This is our event. So it is extremely important that we define the event we are interested in order to consequently define the probability which is given by P. Now we need to discuss how we estimate these three factors. Let me remind you that probability is included between 0 and 1 by definition. We will see the definition of probability. It's a number dimensionless with no dimension, no units, which is included between in the range 0, 1. And then vulnerability is also included. It's dimensionless and it's included in the range 0, 1. Okay. And exposure has the unit of the damage that we are considering. So exposure can be measured in monetary terms, as I said, can be measured in loss of lives. If you are interested in this kind of damage, whatever. It's measured in the units of the damage that we are considering. And exposure usually is included in the range 0, infinity. Okay, exposure cannot be lower than 0. Usually we cannot get a reward if we are hit by a considered event. So exposure is greater, it's 0 or higher than 0, and there is no upper limit. And this is interesting to note. Of course, you may identify situations where there is an upper limit to exposure. But in general, it's hard to say that for natural hazards we have an upper limit of exposure, because you understand, if you get a very extreme event and there is no upper limit to the intensity of a natural hazard, a natural event that is hitting the socioeconomic context, there is no upper limit. We cannot say that an earthquake cannot trespass a given intensity. We cannot say that a flood will not trespass a given intensity. There is no upper limit. So if the event doesn't have an upper limit in terms of its magnitude, then also exposure as a consequence usually doesn't have any upper limit. Okay. Of course, you may say once everything is destroyed, I mean the damage is, the max damage is reached, but it's hard to say that everything is destroyed unless you get the collapse of the entire Earth system. Okay, so usually exposure is measured at the local level and there is no upper limit. So let's talk about the estimation of these three terms, because the equation looks very simple, but the estimation of the three terms P, V, and D is not as simple. So let's start with perhaps the simplest one, which is exposure. Exposure, I remember you, as it is written here, is given by the value of the goods that are damaged, destroyed, if the event occurs. Let me make a selection here. Don't understand. Okay, sorry. Let me make a selection here. E is given by the value of the goods that are damaged, destroyed if the event occurs. And the value of the goods can be estimated once you specify the magnitude of the event. And then you basically, let's talk of an earthquake. You specify the magnitude, like an earthquake of grade 6, okay? Then, given the magnitude of the earthquake, you estimate the number of buildings that are destroyed, and you also estimate the other damages. Beyond the physical damages, you may have other damages like cultural heritage that is damaged, or intangible damages, other intangible damages. So there are some damages that you can easily convert in monetary terms. Other damages are called intangible, means that they cannot easily measured in monetary terms. So think of the cultural heritage. Cultural heritage has a value, and it is an open question, how can I monetize the damage to cultural heritage? So think of the Colosseum. If the Colosseum is destroyed by an earthquake, there is a damage that goes beyond the loss of money for the tourism, for everything. and there is a damage in terms of cultural heritage of people that are used to see the Colosseum and feel like their roots are destroyed if the Colosseum is removed. Okay, so this is called intangible damage, and you can make an effort to convert the intangible damage in monetary terms, or if you cannot convert it in monetary terms, you can make a separate risk estimation. So basically, as I said, you, depending on the magnitude of the event, you try to estimate the goods that are destroyed, the goods and the values in general that are destroyed, and then you estimate their value. So you see that it's an operation, it's an estimation that involves a socioeconomic component. It's a multidisciplinary exercise or interdisciplinary exercise, because of course the definition of the event, of the magnitude, is something that can be dealt with by engineer or by earth scientists in general. But when it comes to the estimation of the number of buildings that are destroyed, yeah, it's still a task for the engineers, but it also includes some more experience, some more expertise than those of the engineers. It already includes, especially if you think of intangible values, it includes a socioeconomic component. And then there is the estimation of the value of the buildings and the intangible values, which is a discipline that is of pertinence of economics. So it's a multidisciplinary exercise. It looks like it is easy, but actually it is a bit interesting. It is a bit challenging, as you can understand. And we are not introducing any model for doing that. The only thing that I wanted to discuss is the definition of the magnitude of the event. And the definition of the magnitude of the event is something that is the key here. Exposure depends on the magnitude of the event. If you get an earthquake that is not very intensive, the damage is reduced. If you get an earthquake with a lot of intensity, the damage is higher. So what is the intensity I should refer to in order to estimate the risk? Okay, of course, the risk depends on the intensity of the event, and what is then the intensity I should refer to? We have legislation that is in a way helping us, because for the design of some infrastructures, and therefore for the design of some adaptation options, we have the legislation telling us what is the magnitude we should refer to. And we will see how this is suggested, okay? The legislation doesn't say an earthquake with a given intensity. The legislation says an earthquake with a given return period. And you understand already, you can perceive what return period means. It means that it's an earthquake that I can expect on average once every return period, once every 10 years, once every 100 years. So the legislation is sometimes helping us. There is explicit reference. For instance, when I want to build levees, and levees are an excellent means for climate change adaptation, levees along a river. When I want to build levees, the legislation for important rivers says that I have to size the levee for a return period of 200 years, which means that the levee should resist to a flood that I am expecting every 200 years, more or less. So the legislation says this. If beyond the legislation, let's say that even if the legislation tells you what is the intensity of the event, you may want to make your design for a greater event, for a more intense event. Why? Because, of course, it's your sensibility, it's the intuition of the scientist that may suggest that you have to go beyond what legislation suggests. You are not allowed to undersize any strategy, any adaptation option below what the legislation suggests, but you can oversize for an event of a more intensive, of a larger magnitude. Why? Because even if the legislation tells you that you are safe enough, by looking at the context, socioeconomic context, you may conclude that you want to be safer with respect to what the legislation suggests. This is the task of the engineer. So this is something that we always suggest, often suggest. So we say to the administrators, look, even if the legislation says that the levee should be 10 meters high, basing on my assessment, I suggest to push it at 12 meters, because 10 meters, in case it is overtopped, means that you are getting a disaster. So no matter what the legislation says. So be careful, we suggest to raise it to 12 meters. And for instance, let's make an example related to climate. Even if there is a protocol that suggests that you reduce your emissions by 2050, like the European Green Deal, which suggests to reach net zero by 2050, if you're involved in an assessment, you may say, look, let's go beyond that. Let's bring Europe at net zero by 2040, because we think, based on our understanding, that it's safer. We cannot wait 2050. Okay, so be careful, because I mean, when you make these decisions, it's precisely your responsibility, your task. So this is exposure estimation. As I said, we don't say more than that, but please be sure that you remember what exposure is. Remember that you be sure that you can define what exposure is. This is a classic question at the exam. What is exposure? And it's also a classic question when you talk to people, when you talk to your to the administrations that are tasking you with a goal. Very often you have to talk about risk, exposure, vulnerability estimation. And by far, when you talk about climate change, adaptation, mitigation, risk is one relevant variable, one relevant index. Okay, so everything is related to risk. You have also to talk about risk. Okay, and when you also listen to the media, they say the risk is that we are flooded. The risk is that, okay, so the media sometimes use the word risk not in an analytical context, not with an analytical meaning. Here we are discussing the scientific part of it, and we are very analytical, but still you have to be able to understand what is the meaning of risk. No matter if the language is the language of the media, of the language of a scientist, you have to be able to distinguish, to understand the difference, okay? Now, we discussed exposure. Let's discuss vulnerability. So, vulnerability estimation is technical. It's essentially technical, and it's a task that it's more or less in the hands of the engineer, in the hands of the scientist in general. Okay, and it is still to some extent multidisciplinary, but it is more contextual. So basically, it is very often a task of the engineer. And in fact, it requires a careful consideration of the protection measures against the considered event. We defined the vulnerability as the probability of getting damaged if an event occurs. So let me make an example. If you build a levee, what result are you obtaining? The result is that if a flood comes, the community is not flooded. The community is not inundated. It means that the event occurred with the same probability P, but the community doesn't care because it's not damaged, okay? Let's instead suppose that the V is overtopped because the flood exceeds the intensity corresponding to overtopping. So let's suppose that it's overtopped, the community is flooded. It means that the levee ensures that vulnerability is 0 up to the flood intensity of overtopping. And it's greater than 0 when the flood is overtopped, when the levee is overtopped. So vulnerability is, once again, defined as the probability of getting damaged if the event occurs. So the event, we assume that it occurs. What is the probability of getting inundated? And given that it's a probability, it varies in the interval 0, 1. We will see the definition of probability later on, but for now, just take into account that is included in the interval 0, 1. Okay, now you may say, basing on your definition, vulnerability is either 0 or 1. You may say that because I made the example of the levee that is not overtopped. At a certain extent, it is overtopped. At a certain intensity of the flood, it is overtopped. And keep in mind that when a levee is overtopped, the levee fails, the levee is destroyed. And therefore, there is like a threshold. Inundation, no inundation. So you may say, vulnerability jumps between 0 and 1. Yeah, this would be indeed an interesting question. However, I may say that a levee fails not only for overtopping. Sometimes it happens that the levee, there is an internal damage in the levee, like for instance, an hole that was digged by an animal. And therefore, you don't know that there is this internal damage. And therefore, it happens that suddenly the levee is not overtopped, but it fails. It collapses. And this possible event cannot be really defined as a threshold because you don't know where the tunnel that was excavated by the animal is located. If it is there, you can define a probability that you get a tunnel by an animal. And therefore, you understand that vulnerability is not just a binary variable 0, 1. It may assume a value of 0.3 if you have a probability of 0.3 that an animal excavated a tunnel in the levee. And this example, be careful, it's very relevant because we are for sure that some of the disasters, some of the inundations have been caused by tunnels excavated by animals. And the reason why these animals are today more active than in the past is also related to climate change, because with increasing temperature, these animals found a better environment where to reach their prosperity, and prosperity means tunnels into the levees. I want to show you a video that one of my colleagues projected at a conference, and which is impressive to prove what is the possible damage given by the animals. And it is very short, or let me say, it is not very short. It's about 4 minutes, but I can shorten it. Let me put it on the screen. And there is my colleague talking in Italian. I'm not sure you can listen it because I'm not sharing the audio, but it's not really important what he says. It's just nice to see what the animal does. And let me magnify it, and let's see. This is called Istrice in Italian, and I don't know how to say in English, I'm sorry. And I think it's something like porcupine or something like that. let's move forward a little bit, and you see the footprint here of the animal, and there are other animals here that are showed, including foxes, and these are animals that use to live in the river corridors and excavate their homes there. Just 1 second. Here it is, the excavation. And you see, it's impressive. It impresses what the animal does. And they basically, in one night, we had an experience that the tunnels were, well, just 1 second, I close it. The tunnels were filled up with solid material one day. 1 day later, the tunnel was again there. And you see what is the length of the tunnel, which is called in technical terms den. In some of the cases, 25 meters, volume is 50 cubic meters, and you understand what 50 cubic meters means. It's like a room. You can stand up in this in these dens. It's really amazing. So let me move the video forward. Once again, see the velocity of the excavation. It's impressive. So here are some pictures. Okay. So you understand that estimating vulnerability by taking into account these also these factors, it's a task of the engineer, but not only the engineer. In this case, it's also a task for ecologists that have to study what is the spreading of these animals. And it is not an easy problem to solve, because you understand, and the detection of the dens, of the tunnels, it's problematic, because you need a physical monitoring in order to find them. And it is problematic to avoid that these tunnels are excavated again. So vulnerability should take into account also these factors. Okay. Okay, now let's turn to probability estimation, which is at the basis of everything. Do you have any question before I move forward? Okay, thank you. So what is probability? So I know that probability usually is a nasty topic for students. So I'm trying to make it quick and easy. But every year that I teach probability, at the end of the year in the surveys for students, you know that there is a question: what is the topic that you understood less, and what is the topic that you liked less? And the students usually say probability because it is a bit nasty. Let's say it's not difficult, as you will see. It's not difficult, but it is a bit nasty. However, it is extremely important that you get some confidence with it, because if you want to get an expert on climate change, you have to get more than expert on probability, because climate change is everything about probability. Climate change is not certainty. We are not certain on how the future climate will be. We can speak in terms of probability. And it is a nice and interesting question how this probability is estimated, because for the future climate, you understand, it's a matter of making a prediction, and predictions are not easy, especially when they refer to the future. So it's a matter of making a prediction, and therefore the prediction is never certain. And you don't have a certainty in the prediction. You have to define probability of what will happen. And this probability needs methods for estimation, because one thing is to define probability, another thing is to measure it. Okay. So far, we said one important thing to start. We said probability is like frequency. So frequency of floods we can use frequency as a synonym for probability. This is true up to a certain extent, okay? And we need to understand actually what is the difference between frequency and probability, but they can be used as synonyms to give the idea. But on the other hand, if you want to be a scientist, you have to understand the correct definition of probability. And understanding means that you not only know it, but you really understand it. It's like understanding how climate works. One thing is to know how climate works. Another thing is understanding how it works. And if you want to be a scientist dealing with climate change, you need to understand, and also for probability. So basically, let's then start to define it, because if I say probability is the frequency of an event, it's not a definition. It's not a rigorous definition, okay? So probability, from a narrative point of view, we can define it by saying that it describes the likelihood of an event that is considered in the considered context. So likelihood means that in the current language, when I say probably tomorrow it will rain, it means it is likely that it will rain, based on my understanding. And probability is quantified as a number, as I said, between 0 and 1. 0 indicates impossibility. When we say 0 probability means impossible. And 1 indicates certainty. When we say probability 1, it means I am certain that this will occur. So probability doesn't exclude certainty, and probability doesn't exclude impossibility, okay? The higher the probability, the higher the likelihood, okay? And there are several procedures involved in the description and estimation of probability. Probability is governed by its theory, probability theory. Probability is part of statistics. What is statistics? Analysis of numbers. You get numbers, typically results from experiments, and you study these numbers in order to elaborate your prediction, to elaborate your understanding of what's going on. A part of statistics is called probability. Okay, statistics is not only probability. But let's say that for dealing with uncertain event, probability is the method that is more largely used. You may ask me, what are other methods? You may have heard of fuzzy logic, machine learning. These are other methods. If you want to make a prediction, you can forget probability theory and you can use machine learning. Machine learning gives you a prediction and a measure of uncertainty. Machine learning is more complicated than probability. It is easier to apply because if you go on ChatGPT and you write a question like, given these numbers, can you suggest a machine learning method for making a prediction of these numbers? And ChatGPT drives you quickly to the solution. So application of machine learning may be even easier than probability. One may say that even for probability methods, you can get indication by ChatGPT. But okay, machine learning can be easier, but understanding what it does, it's more difficult. And don't forget with this word understanding. If you are a scientist, you are responsible for what you say. So you make a prediction, you use a method, you have to understand what the method does, because otherwise you cannot be responsible for your decision. You may remember the sentence of the court for the earthquake in L'Aquila, where scientists, when scientists were condemned, they were condemned to prison and then they were released under conditions, but they were condemned because they made a prediction wrong, even if they understood their methods. And what I want to say, a scientist bears the responsibility, and I think this is reasonable. So be sure that you understand. So probability is not the only method to make prediction and to measure uncertainty. Let's say that it's the most widely used, and given that you bear the responsibility, be sure that if you don't use it, you have a valid justification. Okay, valid justification may exist. You may say, basing on my experience of scientist, of researcher, or technician, I think it is safer that I use fuzzy logic. Okay, and that's fine, no problem. And but be sure that you understand and you provide a valid justification. So let's first of all say that even if you don't realize it, every day you use the concepts of probability. In your everyday experience, you make decisions subjected to uncertainty. Whether or not to take the car rather than the mobike for reaching the university, basically you evaluate pros and cons, you evaluate cost and benefits, and then you make a probability assessment. So you think probably it's faster if I take the mobike. On the other hand, it probably I may get a cold if I take the mobike. So you put together all of these things, and without realizing it, you estimate the probability of the travel time, the probability of getting a cold. You put them together in your everyday life, and then you decide whether or not to take the umbrella when you go out for a walk. You look at the sky, and then you look at the weather prediction, and then basing on your understanding of uncertainty probability, you decide. And then you decide whether you want to stay on the safe side, or if you want to take the risk of going out without the umbrella or not. You evaluate the damage, you evaluate the exposure, you evaluate its vulnerability. Do you have a coat? You don't have a coat. The coat is waterproof or not. These are all parts of risk assessment, risk evaluation. In your everyday life, you do that. And then let's say that when you take a decision, you can be analytical, very rigorous. Like you get in front of a cross with your car and you have two ways, left and right, and you make a rigorous assessment of travel time, of whatever is influencing your decision, and then you make like an analytical estimation that brings you to decide. Or you may get in front of the cross, you see two ways, and you say, I like more the right way. You forget about, you don't care about travel time, about the cost. You like it and you go for it. There are many people deciding like that. And also in climate change adaptation, you may decide like that. Of course, be careful of the responsibility that you bear, as I said, okay? But there are several ways to decide, okay? And also in probability estimation, you will see that there is some subjectivity. So let's introduce what is probability in a quick way. And what follows, look at the selection on the screen, is not a formal introduction to probability. And it's an informal introduction. Why informal? Because I want to be clear. I want to give priority to clarity. And also, let me say, I'm not a statistician. I'm not an expert in probability theory. Yes, I studied a lot of probability theory, but I don't know everything. It's like R, you know. I'm not an expert of R. I'm not an expert of Python. I studied and used a lot them, but you may reach a better understanding than mine. And the same for probability theory. I want to be very quick. I want to be clear. And you may, if you are interested, of course, you may gain a better knowledge, a more rigorous knowledge, okay? For technical purposes, I think that what I'm saying is enough for taking the technical decisions. If you want to make innovation, if you want to propose new methods, then I think you need probably more than what I'm teaching you, okay? Just to be very clear. And to be very clear, there is much, much more on probability theory with respect to what I'm teaching you. So to informally introduce probability, we need to refer to a given event, a given hazard, okay? Earthquakes, floods, or industrial explosion, or car accident. And given that this event is subjected by uncertainty, we define it as a random event, a random event. Look, there is a link here. Let's click on it. Okay. Once in a while, we need to random event definition, how to find probability. What is a random event? A random event is something unpredictable. Okay. Unpredictable doesn't mean that you can get an indication. Unpredictable means that you cannot reach certainty. Sorry. You cannot reach certainty. Okay. So unpredictable means that you can make a prediction, but is affected by uncertainty. For instance, a typical random event is tossing a coin. You can make a prediction. The outcome is either head or tail, but you cannot, given a single flip, you cannot say that the outcome will be head. Okay. As it is unpredictable, you can never give it an exact value. Okay. Exact. For example, you couldn't predict the probability of falling down a flight of stairs in the next 10 years, okay? As it's a completely random event. The opposite of random is deterministic, which means that you can perform an exact calculation, okay? Let's go back here. So it is an event that is not predictable with deterministic approach. So deterministic means a relationship which is correct, which is precise. All natural hazards are associated to random events. Okay, you cannot identify a natural hazard that will occur with certainty. Okay, I would say that in general, all of the hazards are related to some uncertainty, because you can think of a car accident. It's highly uncertain. Of course, you may get in some conditions certainty, like I go out with the car that is heavily damaged. I am dead sure that I will not reach destination before the engine crashes. But it is a very, very specific situation, very unlikely in our everyday life. Usually we are exposed to events that can cause damage, either natural or whatever, and they are random events. Climate change is for sure random. Okay, we don't have certainty. If you look at climate scenario, we have already seen that we have several projections, and each projection is indicating a different trajectory. It's random. Okay. So typical events of random events, not natural, are tossing a coin or rolling a dice. These are two very nice examples. Okay, tossing a coin, there is a link here. Okay, coin flipping is so nice, so relevant that it's also in Wikipedia. And we know what is. And keep in mind that there has been a lot of experiment in statistics based on tossing coins. Okay, rolling a dice, it's very similar. The difference is that you have 6 possible outcomes. Okay, so what is the first step? If you want to analyze a random event, the first step is to identify all the possible outcomes. And all the possible outcomes build up the sample space. We call the sample space the pooling of all the possible outcomes. Okay. For coin tossing, if we exclude the outcome that the coin stands on the side, on the edge, what is the sample space? It's formed by 2 outcomes, head, tail. Very good. Be careful. These 2 outcomes, head or tail, are mutually exclusive, which means that you cannot get both of them. You flip a coin, you either get head or tail. So you learn here what mutually exclusive means. Okay. Okay. So let me ask you this question, which is written here. And let me hide the result. Okay. By taking into account that probability is expressed by a number in the range 0, 1, as we anticipated above, just 1 second, okay, perfect. Where 0 means impossibility and 1 means certainty, what is the question that I would like to ask you? The question is, what is the probability of getting ahead from a coin tossing? Okay, and I think you have the answer. Let me just see on the chat because I see a red here. And okay, there is a question. With how much data we are able to move from a random-based approach to deterministic approach in climate change? I don't think it is a matter of data availability. So data availability means has an impact on the uncertainty of your prediction. If you base your prediction of an extended information, you reduce uncertainty. But the nature of the prediction, probabilistic or deterministic, it doesn't depend on data. Because if it was only a matter of data, we would say that provided we have information, this is a deterministic process. And but I mean, it's not the amount of the information that makes the difference. The amount of information makes the difference in terms of uncertainty. If the prediction is probabilistic, it means that you have uncertainty. If you have a lot of information, then you reduce uncertainty. There are some people that say that any prediction has a deterministic part and a random part. Yeah, I think this makes confusion. And let me give you an example. If I toss a coin, for sure, with determinism, I can say that the outcome will be either head or tail. This is deterministic. There is no uncertainty. Okay. And if you toss the coin, you cannot say what is the outcome with certainty, but you can say that it will be more or less half of the cases a head and half of the cases a tail. So you see that there is some determinism here. It's not completely random. It's not that you cannot say anything on the outcome. You can say something, and that something is usually gained through a deterministic reasoning, but then there is still uncertainty. But I prefer just to split in two categories. Do you have uncertainty? This is a random process, a random prediction. Do you have determinism? Okay, if you have determinism, the prediction is not random. I will show you an example of what I mean, but let me conclude to answer to your question. When you talk about future climate, there is no determinism. You have models, but these models are uncertain. So you have some deterministic component, but it's uncertain. Okay, so my question, what is the probability of getting a head or getting a tail? Okay, probability is split between 0 and 1. The sample space is given by head or tail, so only two possible events that are mutually exclusive. You understand by intuition that probability of head is 0.5, which is the same as probability of tail. So 0.5 plus 0.5 makes 1. This is a possible definition, and you may also say, but it's clear, the probability is 0.5 because I have to split certainty, which is 1, and I am certain that it's either head or tail. I have to split it by 2. So it's 0.5 and 0.5. Okay. Yeah, this is a possibility to estimate probability, and we didn't make any experiment. It's just based on our understanding. So you see that the prediction is useful because it's not like I toss a coin and I don't know anything of the possible outcome. I know a lot of it, because I know that with probability of 0.5 I get a head, with probability of 0.5 I get a tail. And you may say, okay, but this doesn't give any additional information. Yeah, but think of climate change. If I get probability 90% that the future will be much warmer, like +2, above +2 degrees with respect to the pre-industrial period, probability is 90%. This is a relevant information, because I am almost sure. If I am given, yeah, it may be above 2 with probability of 5%, then you understand it's very unlikely. So it's a prediction that is very useful. So the example of tossing a coin looks like something that I already know. But if I am given the probability for something that it's unknown to me, like future climate, this is great. It's a useful prediction. It's not useless. I mean, engineers are used to deal with uncertainty. Any estimation, when we estimate over a building the load given by snow, I mean, it's uncertain, but still, it's very useful that I know what is, with very large probability, the load caused by snow over the roof. This is very useful. Okay, just in order to make the explanation more fun, let me turn to R console, okay, R Studio console. So let me shift the screen. What you see now on my screen is R Studio. I suggested to you to install it. What is the advantage of R Studio with respect to the only R console? R Studio, you see, presents to you a screen with several windows. You see 4 here, but you can also add windows. You can size them and you can shift the boundary between windows as you like. One of the windows is the console. You recognize here on bottom left, look at my mouse, the R console. I am now selecting the introductory text. And so you have the console here, but you have the other windows providing additional information. For instance, here you have a window where you have 4 possible alternatives. By default, you get the environment. Environment means that you have a list of the data. So if I include an additional variable, a equal 1, look at what I'm writing on the console, you see that in the environment, I got in the list the presence of a. If I remove a, then you see that a disappeared, which is nice. I mean, this window. Also, I have a plot window, which is interesting. The 4th window, you see that there are several alternatives. One of the alternatives is the plot. So if I make a plot, look at the console. I'm now clearing the console, okay? Control L. Look at the console, plot 1, and you see the plot window appears. And it's included into R Studio. You don't have to shift from one window to the other, which is nice, okay? And now, let's look at the top left window. It's the script window. It means that you can type the instructions into R into the script, like a equal 1, okay? And what is the advantage? The advantage is that you can save the script as a text file, and you can repeat it for another time. In principle, you could do it also with the console, but here it's easier. So let's suppose that I want to define 2 variables, a equal 1, b equal 3, and then a third variable, which is given by a plus b. Look at what I'm writing in the script. This is not executed. First, you can save it, okay? So you have icons here for saving. So let me save it. And it doesn't ask me the name of the file because I already saved it before. But if you choose Save As, you see a Windows with that asks you the file name and also the location. You can put it in the directory. Very good. Now, if I want to bring these instructions to the console, and then let me add the value of C, okay? What I can do is either run them one by one. So if I click on run here, look, you see the console A equal 1, and then I got in the global environment the name of the variable. And then the script advanced to the next run, B equal 3. Or what I can do is to source the script altogether. Okay, let me click on source. Okay, and you see here that also I got the C value, and which means that everything was executed. Okay, if I remove, sorry, I go to the console, I remove the three variables, A, B, and C, and I want to repeat the script, I go in the script window and I click on source, and that's it, and they are back. Okay. So the script may be useful. You may decide to write on the script and then pass to the console the instructions that you want to save, while you can type directly on the console the instructions that are just temporary. Like, I mean, if I want to make a plot of C, okay, and I don't want to save this instruction, I go directly to the console and I get the plot of C. Good. Now let me remove A, B, and C because I'm not interested. And then let me clear the console, and then let me also clear the script. So I mentioned the experiment of tossing a coin, and let me go to the console. Can we reproduce such an experiment into R? Yes, of course. First of all, let me start by saying that in R you can generate a random number, runif, in the range 0, 1 by using the function runif. So runif, and you give as an argument the number of variables that you want to generate. Run unif 1, you see the result is 0.25. If I make it again, arrow up, now arrow up to get the last instruction, you see other random numbers. If you want to specify a different range, you can put 0, 2. And you see now the range is 0, 2. It's generation of a random number. Are you following me? Do you have any question? Okay, now let's make an experiment. I clear the console of tossing a coin. So let me generate a random variable in the range 0, 1, and let's round it. Round means nearest integer. 1, 1, 1, 0, 1. This is the experiment of tossing a coin, where 0 is, say, head, and 1 is tail. And if I want to make several experiments, let's bring the number of the variables to 10, and you see the result. Okay. Okay, so what I did here is 10 tossings. 10 tossings. What is the frequency of the tail? 1. Okay, I said tail is equal to 1. Okay, what is the frequency of ones? In this case, it is given by the number of ones, and they are 6, divided by the total number of tossings, which is 10. So the frequency is 6 divided by 10, 4.6. This is the frequency. I can compute it directly. Let me call back the instruction, and let me compute the sum of it. And then let's divide the sum by 10. Is this clear what I'm doing? I'm counting with the sum the number of 1, and I divide it by 10. It's again here 0.6. Now it's 0.3. Let me make other attempts. 0.7, 0.3, 0.4. Uncertainty. This is uncertainty. Over 10 attempts, I get different frequency estimates. And here you can say something that expresses a reflection. I said in the past, probability is a synonym of frequency, but I am expecting that the probability of tail is 0.5. Here, I see that the frequency is never 0.5. So this brings us to a conclusion. Frequency is an approximation of probability. Frequency is an estimate of probability. And the uncertainty of the estimate is decreasing, I am expecting, decreasing with increasing data. And I connect to your previous question, Abbas. So 10 tossings mean a lot of uncertainty. If I tossed like 1 million trials, I am expecting a lower uncertainty because I have more information. The prediction is still random, but I have more information. The frequency with more information approximates probability much better. Let's do that. Let's do 1 million. Okay, and I need also to divide by 1 million. See, 0.49, 0.49, again, 0.50, 0.50, 0.49, 49, etc., 0.50. You see? So with increasing information, increasing number of tossings, you get very close to probability through the frequency. This means reduction of uncertainty. Let me try to make an experiment by 1 billion. It takes some time, of course, because 1 billion numbers. This would be impossible to be made in Excel. I hope that it doesn't saturate the memory of the PC, but what I am expecting as a result is that it is close to 0.5. Okay, let me just interrupt it. Okay, now it doesn't interrupt. So let's wait for the conclusion. Okay, you see 0.5. Good. So what did we learn? We learned how to estimate probability. Probability can be estimated by making experiments or by intuition. If you make the experiment like I just did, this is called frequentist estimation. You assimilate the frequency to probability. This is fine. They are synonym, provided you make a large number of experiments. And or you can estimate it by intuition, because we understood that probability would be 0.5 preliminarily, and this is called Bayesian estimation. So sometimes it's important that you remember that, because sometimes also on the media you listen people talking about it was estimated through a Bayesian approach. It means like the elections, the outcome from the elections, you cannot make an experiment. Okay, you can take the exit polls, but still it's not a real experiment. You cannot repeat the election. You cannot make the election 10 times. So you make an estimate basing on intuition, information that corroborates your intuition. This is Bayesian estimation of the outcome. It is extremely useful, okay? And in natural hazards, you can make experiments, because if you look at historical data, like for instance, probability of getting an earthquake, you get the historical data, and the historical data are like experiments, because you get information on maybe 10 earthquakes that occurred in the past 200 years, and you know the intensity, and these are like experiments because you had 10 earthquakes, so you can make a prediction based on the frequency that you observed. If you don't have historical data, then you have to make a prediction by looking at the geology, by looking at the tectonic faults, and this is Bayesian estimation. Okay. Now, let me give you another example. Rolling a dice. Let me clear the console. So again, let's write it from scratch. So first of all, let me generate 1 million numbers in the range 1, 7, and then I have to round this generation at the lower integer through the function floor. Be careful of the parentheses. RStudio helps you. You see, when I close a parenthesis, it gives to me indication of the parenthesis that is associated. Okay, so this is a generation of random numbers between 1 and 6. Let's make the example of 100, and you see. So what is the probability of getting a 1? Now, let me compute the probability of getting a 1 in this way. Let me define a variable like a, which I assign it's a vector, the outcome. Okay, so a is here. Now I can estimate the length. Be careful of what I'm writing, the functions that I am using. You have also the video, everything is recorded here, because these are useful to you to learn. Okay. Okay, now length of a, but let's put a condition. A equal 1. In this way, you see the syntax. Okay, the number of ones is 21. What is the frequency? It's the length divided by 100. You may do this. Instead of dividing by 100, divide by length a. So this is the probability frequency, which I assimilate to probability of getting 1. However, what is the probability of getting a 1 in rolling a dice? The sample space is 6. The events are mutually exclusive. So the probability of getting a 1 is just 1/6, which is the same as the probability of getting a 2. So what I am expecting is 0.16. Okay, good. Let's see if by increasing the number of rolls, I can approximate 0.16. Okay, let's first generate another vector A with 1 million. And then let's compute the probability. 0.16. You see, it's the frequency estimation is perfect. The outcome is uncertain, but we can estimate the probability based on the data in a very precise manner, provided I have the data, of course. Okay, let's now go back a little bit to the theory, but let me anticipate one thing. So far, we dealt with discrete variables, 0, 1, and rolling a dice. It's discrete. Let me anticipate a complication. Let's suppose that you have a real variable. And so let me just do this experiment. See, let me generate this random variable 1 million by removing the floor, the function floor. If I remove it, the result is real numbers, not integer. Let's suppose that let's show the first 10 numbers of A. You see, real numbers. Okay, now let's suppose that I want to estimate the probability of getting a value of 3.0. 3.0. And let's suppose that I want to use the approach that I used before. So what I do is length A with the condition A equal 3.0. What is the length? Is 0. Of course it's 0, because when I generate real numbers, they have an infinite number of digits, so I will never get the variable that is equal to 3.0. Never. So what is the conclusion? That the probability of getting a value of 3 is 0, which is unrealistic. It's unrealistic because I know that there are several outcomes that are not really 3, but are very close to 3. So I cannot say that the probability of getting an outcome of 3 is 0. I have several numbers that are very close to it. So from a technical point of view, here I have a problem. So let's forget about this problem and let's stick on the discrete events. Okay, let's stick on that. But I anticipate in the future we will need to discuss this. Okay, let's go back. Let's go back to the our web page. And what is written here is what I already discussed. Okay, over R. When I make a selection, the formulas are not selected, so be patient. Okay, now, so we can write equation 2, which is the translation in mathematical terms of the computations that we did. So the probability is given, the probability of getting a value h is given by the number of outcomes that are meeting h, that are equal to h, divided by the total number. Okay, and let me say that here with this equation we are forgetting, because it's written somewhere, we are forgetting to specify that n total must be large. Okay. Okay, now given that we understood how probability is estimated, given that we understood that probability is equivalent to likelihood, how can we define it in rigorous terms? And this was a challenging question for statisticians about 1 century ago. And they wondered indeed how probability can be defined. And they provided different definitions. The definition that is today accepted is that was proposed by Kolmogorov, a famous Russian statistician. And it is based on Kolmogorov axioms. So please learn them, because this is what we accept as definition of probability. Axiom 1, the probability of an event is a real number greater than or equal to 0. Very easy to remember. Axiom 2, the probability that at least one of all the possible outcomes of a process, such as tossing a coin, will occur is 1. I try to explain better. When I toss a coin, the probability of getting either a head or a tail is 1. Okay, so if you get the sample space, the probability of getting an outcome that is equivalent to at least one element of the sample space is 1. Okay. Axiom 3, if two events A and B are mutually exclusive, then the probability of either A or B occurring is the probability of A plus the probability of B. The The first two axioms basically reflect our assumption that probability lies in the range 0, 1. If you put them together, you obtain that probability is in the range 0, 1, okay? The third axiom implies that the probability of a head when tossing a coin plus the probability of a tail is 1, okay? So once again, remember these three axioms. They give a rigorous definition of probability. What does this mean? Whatever you estimate probability, you have to make sure that your proposed estimation method meets these axioms. If you estimate probability through frequency, this is perfect. It meets them. If you make a prediction, a Bayesian prediction, outcome from an election, you have two candidates. You cannot say candidate A has 60% probability to win and candidate A has 45% probability to win. You cannot say that because 60% plus 45% is, the sum is 105%, which is larger than 1. You cannot say that. Okay. If candidate A has a 60% probability, then candidate B has 40%. Okay. And this also means that you can estimate the probability of something occurring by computing a difference. I give you an example. I made the example of the flood exceeding the level of the levee. Okay. Perfect. If the probability of exceeding the level is 0.1, what is the other possible outcome? The other only possible outcome? It's that the levee is not exceeded. And therefore, if the probability of exceeding the levee is 0.1, what is the probability of not exceeding the levee? Is 0.9. It's a difference. It's 1 minus 0.1. Okay, I think that what is written here was already discussed. So I think it's okay. It's interesting to see this exercise here. For the event of rolling a dice, what is the probability of getting an outcome lower or equal to, say, 4? Okay. Now we can write the additive rule for probability. Probability of outcome I less or equal than 4 is given by, they are mutually exclusive. So probability of 1 plus probability of 2 plus probability of 3 plus probability of 4. So it's each probability is 1/6. So the sum of the probability is 4 divided by 6, which means 2/3. What is this? It's probability of not exceedance of 4. And this is called cumulative probability. When we talk about probability of not exceedance, it's called cumulative probability. And this is interesting because, as I said, for floods, we are interested in the probability that the water level doesn't exceed the level of the levees. Okay, here there is a figure that I leave to you to understand. It's the probability of the sum of two dice rollings. So it is explained in this figure. This figure shows all the possible outcomes. And I mean, again, the event is the sum of two dice rollings. So if the sum is equal to 2, you have only one possible combination, that with the first rolling you get 1 and the second rolling you get 1. It's only one possible combination. So given that all the possible combinations are 36, the probability of getting 2 is 1/36. What about 3? 3 can be obtained with two combinations. First rolling 1, second rolling 2, or the other way around. First rolling 2, second rolling 1. So you have two possible combinations. 2 divided by 36 is the probability. 4, you have three possible combinations. 1, 3, 3, 1, 2, 2. 3 over 36. So complete this understanding. Complete it, okay? And you will see that the possible outcomes are these listed here on the horizontal axis. The max is 12, of course, only one possible combination, 6 plus 6. And you will see that the sum of these individual probabilities is 1, must be 1, okay? So the sum of 2 plus, the sum of probability of 2 plus probability of 3 plus, etc. You make the sum of these 1 over 36, 2 over 36, 3, 4, 5, 6, etc. And then you get 1. And I leave to you the inspection of this figure because it is in a way trivial, okay? Good. So here there is a box which gives to you the instructions for computing for making the experiments in R, which I just did, okay? And we already discussed this, okay? Okay, perfect. So for the discrete variables, we are done. We know what is probability, and remember, the question, how would you define probability? You have to reply with the three axioms of Kolmogorov's. To the question, how would you estimate probability? You have to reply with two possible answers. First, with the frequentist approach. Second, with a Bayesian approach. And you are done. This is what we discussed today in 2 hours. Okay, you are done. With the discrete variables, you are done. But as I anticipated, what we learned today fails when you deal with continuous variables. So let's focus on the case of the continuous variables. And I just want to start today, but we don't finish because we have about 7 minutes to go. Before I go forward, questions? There is an interesting question that I may ask you. I'm not sure whether you will be brave enough to reply. And the question is, do you have any idea on how the challenge of continuous variables can be solved? By, of course, using a similar approach to what we did for discrete variables. So given what you learned today, if I told you, like in RStudio, this problem, if I mention to you this problem, I want to get the probability of 3 for a continuous variable in the range 1, 7. And but if I get the frequency estimation, I can't apply it because it's a 0, as you see on the screen. So the interesting question is, do you have any idea? I mean, an engineer, if it is asked such a question, an engineer is very pragmatic. Maybe that the engineer doesn't know the theory really well, doesn't know mathematics, but an engineer is very pragmatic. So the answer for an engineer would be very easy. And the answer is, no, it's too early. Gaussian distribution is too early because basically probably you have already some background of probability, so you skipped several steps. What I would say is I'm not interested in so many digits, so let me round it. And then if I round it, I mean, if I round the variable to an integer, of course, the problem is solved. And I may say I'm not interested in the digits because if I wanna compute, for instance, probability of a flood, and the flood is, the intensity of the flood is given by river flow, I'm not interested in a river flow of 1.5. I'm interested to know if it is 1 or 2. The 0.5 is not technically relevant. And therefore, if you round the variable, basically you solve the problem. And from a practical point of view, it's very easy. And or you could say, I'm interested in flooding. Okay, but in flooding, I'm interested in the probability of the river flow exceeding the levee level. Let's forget about the animals, okay? The dams, etc. I'm just interested in the levee level. So let's suppose that in this case, I generated this A variable, 1 million data, and the levee level is corresponding to 5. So let's compute the length of A greater than 5. And you see that I get a probability. The probability is, if I divide for 1 million, probability is 0.33, not surprisingly. It's not a surprise. It's 0.16 times 2. Because the probability of greater than 5 is given by numbers that are greater than 5 and greater than 6 is 2 over 6. 2 over 6 is 0.33. And so an engineer may say, I'm not interested, I'm just interested in the probability of not exceedance in the or exceedance. The probability of exceedance is 0.33. If I wanna get the probability of not exceedance, easy, 1 minus. And I say not exceedance because you may say, but I'm not interested in not exceedance. The risk is generated by exceedance. Yes, that's true, but in technical computations, usually when we talk about cumulative probability, we mean probability of not exceedance. So you don't have to be concerned. Not exceedance is the same as exceedance. It's just one minus the other. Okay, so this is the solution that you could suggest. Either I round the variable, or I am interested in the probability of exceedance. However, in estimating natural hazards, you may be interested in some more than the probability of not exceedance. You may be interested in the probability of getting really a precise number, like 3, as I did before, okay? Like I did here. And look at my mouse. And sometimes it happens. So, I mean, the problem is not completely solved. It's solved for the applications where I need a probability of not exceedance or exceedance, which is the same thing as I said. It's not solved for the applications where I really need to know the probability of getting a precise number. And so in this case, I could use indeed the rounding approach, but I need something more rigorous. Okay, let's stop here for today, and then on Monday we don't. Monday we don't have lectures because it's degree day. Look at the calendar and be careful of that. I'm not sure whether I sent an email. I need to check in Virtuale to remind you that we don't have lectures on Monday. I don't think I sent it. I'll send it. I sent it to the other students, but not to you. So remember that. We meet again next Thursday and virtually. We don't meet on Monday. And if you look at the calendar on my website, it's updated. It was already updated at the beginning. Do you have any question? Looks not. So let me stop the recording and stop